All right. Okay, so we're going to wrap up chapter 29 today on magnetic forces on wires that are carrying current. And then we'll talk a little bit about the various different applications and weird stuff you can do with magnetic fields now that we understand how they work. Okay, and then I'll give my little spiel about how magnetism comes about and where it comes from at the fundamental level. So I'm going to clean my glasses first though. Okay, so one thing we may be talking about so far is that, we can figure out the magnetic force on a charge, right? Remember the Lorentz force, or easier to remember, just call it the magnetic force, right? We can calculate what that is, right? The force of a magnetic field is just Q times V cross producted with B, where Q is the charge of your thingy, right? And then V is the spot velocity, and cross producted with the magnetic field, right? So, and as usual, when you have to deal with the cross product, don't do it using crazy math stuff, right? Just calculate the magnitude first, and then use your right hand to figure out the direction, right? Okay, what we're going to do today is we're going to explore how that affects charges that are moving in a wire, right? If you have charges moving in a wire, that creates a current, right? So the same thing happens to a wire. If you put a wire in magnetic field, it will also be affected by it, because as long as there's current moving inside, that means there's actually charges moving inside that wire also, right? Okay, so we're going to try to convert basically the magnetic force equation, which is the charge times the speed cross producted with the magnetic field, by just picturing this little cylinder picture where we're like zooming into what a wire looks like and what the charges inside are doing. Okay, so if you have just think of a little parcel of a charge with some charge Q, right? It has some length L, right? And it's moving, right? Remember, charges move through solid matter with this thing called the drift velocity, right? It's a pretty slow drift velocity, but there is charges moving, right? But let's say if you have this wire in a magnetic field, right? The charges, right? Once again, right? We're going to do the magnetic force is QVB, right? So we'll count with our first finger the velocity direction. The magnetic field is into the board, right? And if we know it's not true, but assuming that it's just a positive charge moving inside these wires, right? We're going to have a magnetic force going up. Okay? So all we have to do is really convert this charge times velocity, right? And we actually did this before already, where the charge times velocity is actually just the magnitude of the current, right, times the little segment of wire, right? Where now this is the length of this wire here, right, is delta S, right? Delta S. And it's a vector because it can, this little segment of wire can be pointing in any direction you want, okay? And so when you do this with charge times V, where it converts to the current, the magnitude of the current times this little segment of it, right? When you have a long wire of some length L, let's say, right? And that this wire kind of have to be pretty straight, okay? Then you can convert this magnetic force equation on a single charge to a magnetic force equation on a wire, okay? And this is valid as long as this wire is straight, okay? Okay. Right. So this is the magnitude of, well, the value, like the scalar value of current. It could be positive or negative, right? And L, right, is now this weird vector L, where it's the length of the wire. The magnitude is the length of the wire, but then the direction is the direction that the wire points. Okay? And then the magnetic field is the same magnetic field we had to deal with before. Okay? So let's take a look at some cases, right, where we have some current going in the wire and some magnetic field. Okay? So in this case, right? Can we figure out what is the direction of the magnetic force, right? So if we have, once again, L, which is the vector, you use your first finger, right, your thumb, and then you cross product it with, well, in this case, there's no way for me to cross product it because, right, it's in the same direction, right? If L and B are in the same direction, what should be the magnetic force? 0, right? So force on the wire in this case is actually 0, okay? Right? It's easier to see if we can have, once again, right, I think the book gave you the answer, unfortunately, right? But if you do the cross product between L and if the magnetic field is going into the board now instead, right, you have L going this way and then magnetic field going into the board, and then so the force is actually going to be pointing upward, okay? So this is the direction, right? It's going to be, let's say I set my X and Y axis like this, right? It's going to be in the J hat direction, right? And to calculate the magnitude, right, once again, you do the magnitude and the direction separately. It's just the magnitude of the current, the length of the wire, right, times the magnetic field sine of the angle between the wire and the magnetic field, right? In this case, it's 90 degrees, so it actually comes out to be a factor of 1, okay? So you can imagine this can be a useful thing if you have a wire and a magnetic field. It somehow lifts things up, right? And so you can, so in the book, I'm not going to go through it since the book already does it, right? You can do a little magnetic levitation, okay, where you can lift objects by just running a current through a wire, right, inside that's actually embedded into a magnetic field, right? And this is basically how a lot of these things called maglev trains, right? So they what they do is the train itself is actually the magnet, okay? And then they run current along the track, and if you do that, then you can actually lift the train up off the ground. So the train itself and the track are not touching each other, and therefore you reduce the amount of friction on the track between the train and the track. And all you have to do is actually deal with the air resistance, right? That's why these trains are these weird bullet shaped, right? Okay, and these maglev trains can reach up to like 400 miles per hour, at least the ones in Japan and maybe in Europe and in China. And these little crazy shape maglev trains are utilized to basically go around pretty fast for a hyperloop. So the hyperloop is kind of a different idea. Um, I'm not sure what the current design of the hyperloop is, but the idea of hyperloop could also have magnetic levitation in it. But the idea of hyperloop is also to put it in a tube that is a vacuum, so it also removes the air resistance. Okay, we'll see how realistic that is. Yeah, Alan.
How would they break maglev trains?
How did they apply brakes? Oh, that's an interesting point. Um, so let's think about what happens. Okay, so um, so let's go up to this drawing here, this example here, right? So we can, if we have a current going this way, right, there'll be a magnetic force pulling up to offset the force of gravity, okay? So if you want to, this is actually something we're going to cover next chapter called electromagnetic induction. So what you can do is, I'm trying to remember, there's also, so these wires, right, is actually a loop. So I'm going to try to draw one on the train, okay? Okay, so we have a train, and this is my best drawing of a train, right? And the train, right, has magnets on the side of it that maybe creates a magnetic field that's going into the board, okay? And what the track is actually, there's a track that runs wire that runs current through it, right? Okay? These current doesn't have to just go straight. It can also have one that are, like, I'm trying to figure out which direction it is. You can also have it kind of go in a little loop in here. Well, that's probably not the right place to draw it. But with these magnets, there's also, you can draw a little wire loop that's not connected all the time. And what happens is that when you run current through a loop like this, it'll create this thing called the electromagnetic induction, and actually like basically just bring energy out of the train itself. We're gonna see this when we play with this when we come back from spring break, unfortunately. Okay, so there is magnetic braking that you can use. Okay, so that's a really good point. Okay. But there's also physical brakes, just in case there's an emergency stop. They just, metal to metal type of braking, right? Yeah. Okay. But this type of magnetic braking is nice because you actually recover the energy from the kinetic energy from the train. Okay. So we'll get to see that next time. Yeah. So come back after spring break. Okay. So now that we figure out that, well, if you have a magnetic field, you have a wire going through it, right? If the magnetic field is perpendicular to the wire, right, you're going to have a magnetic force, right? But what if you have two parallel wires next to each other? What happens then? Let's say I have some wire 1, right, that has some current going through it, right? Right, say I times L, right? And then we have another wire that has no current, right? Let's say at the beginning there's no current going through it, okay? Well, if you have a wire with a current, this actually creates a magnetic field around it, right? That's one of the first things we learn about magnetic fields, that if you have current, it creates a magnetic field around it, okay? So using my little right-hand curl rule, right, if the current is going this way, we expect the magnetic field to be coming out of the board and then into the board down here, okay? So I'm going to try to draw that, right? So this is coming out, this is going in, it's going this way, it also goes behind, right? Okay, and there's also a bigger loop like this, right, where it comes out, and then it actually goes through the other wire, right, right, and then goes back behind there, right, and then reconnects back up here, right? So wire number 1, the magnetic field of wire number 1, right, right, is impinging, right, affecting wire number 2, right? But if there is no current in wire number 2, nothing happens, right? Because if your charges are not moving, there's no magnetic force, right? But what if you have a current? I'm going to call this I1, I2. Oops, I just need to change the I. Okay, it has the same length, let's say. Okay. What happens then is, now that you have a current, right, in a magnetic field, that means there's going to be a force on it, right? In fact, if the current was going to the right, once again, we're going to do the magnetic force on a wire, right, which is, oops, the current magnitude times the length vector of that wire, cross-producted with the magnetic field, and guess which way the force is going to be applied. Okay, so once again, we use the right hand, right? L is going to be in this direction, B in below, the other wire is going into the board, right? Okay, so therefore, there's actually a magnetic force pointing up. Okay, force of 1 on 2, right? That's actually pointing up. Okay, now that we have a current on wire number 2, what happens? What else should we be modifying in this situation? What's happening to wire number 1 now? I'm sorry? It's not sure. The currents are separate, but what could be emanating from wire number 2 now that we have a current going through it? It creates its own, right? Current number 2 also creates a magnetic field, and that magnetic field will also affect current number 1, right? So this is like a like a self-inducing, self-fulfilling prophecy, right? Where, right? So in this case, right, I'm gonna draw in maybe purple color, right? So we can see the 2 different magnetic fields, right? Once again, using our right-hand curl rule, we can figure out that, Well, there's going to be a magnetic field coming out of the board here, right? And then going into the board down here, right? Right. So I'm going to complete this little circle. Okay. 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 So when the magnetic field gets up to here, is coming out of the board here, right, and going into the board here. I'm going to try to keep drawing these circles in a not silly way, even though it might look kind of silly, right? Right now, there's a magnetic field affecting current number 1. Now, which way is that going to point? I'm not going to do that this time. You guys have to do it, okay? You have to tell me which way it's going to point. Which way is force due to wire number 2 is applying on wire number 1? Is it going to the left? Is it going to the right? No, right? Is it going up? Which way is the force? Use your right hand. Right? Right. How many think it's up? How many think it's down? Okay. So 5 of you guys have a right hand that works. Okay, good. So let's use our right hand, right? So we have our current still going in this direction, but instead of going into the board, now the magnetic field is coming out. So therefore, the force is actually downward. Okay. So force of 2 on 1, right, is actually downward. So the 2 wires actually attract each other. Okay. And this is actually one of the reasons why magnets are attracted to metal, and we're going to talk about that in the next chapter when we talk about electromagnetic induction. Okay, so I'm not going to go through all the math because it's just a bunch of algebra steps to calculate the forces on 2 parallel wires. Okay, but the end goal is that you're going to end up with a force that's going to be proportional to mu naught. That's the magnetic constant as usual. So, right. The length of the wire, so imagine, the longer these wires, the more force there is. That makes sense. Multiplied by the current in wire number 1 times the current in number 2, and then divided by this geometric factor 2 pi divided by d, where d is the separation distance between them, right? Remember that magnetic force on a straight wire is inversely proportional to the distance away, right? So that 1 over d factor makes sense, okay? Yeah. Right? So I show you guys, so let you guys just copy down this equation real quick, right? I show you guys that, well, when the 2 currents are going in the same direction, the force is going to be towards each other. They're going to try to pull each other towards each other. When you have a current going in the opposite direction, and unfortunately the book always gives my answer away, right? Right? If you do your right hand rule, once again on your own, you're going to find that the forces is going to be trying to pull the wires apart instead, okay? Because the currents are in opposite directions of each other. Basically, you flip all of your right hand rule, right? And they're going to be pulling each other apart instead, okay? And this is one of the concerns when you have high voltage, high current electrical line that are running in parallel to each other. So if you look at this wire, I need a cable. Anyone have a power cable? Like the electrical outlet ones? Yeah, like that. No, that's not, well, that's not as useful because that's very low voltage. So if you imagine a cable, right? Like a power cable from your laptop, right? There's actually 2 wires, right? Like that, right there. Right? Right? This flat part, right? There's one that's going to be carrying current going this way. The other one's carrying current going this way. If you run enough current through this, they will actually explode away from each other. Okay? And this is a concern when you're carrying, not for your laptop current, but like if you're, if you're running a power station that's, providing the power for like the entire city of Turlock, you have to keep these wires actually kind of far apart so that, they don't exert a magnetic force on each other and then try to pull each other apart. Okay? Oops. Where's my pen? It's right there. Okay. Thanks for bringing that out. Okay. So that's how you calculate the magnetic force between 2 current carrying wires, okay? And there's a neat application of this. This is actually how a lot of electrical scale works. Okay, so the way the electrical scale works is that you have a little spring, right? Normally you can just read out the position of the spring, but these scales are like so flat that you cannot use it to read out, right? So what they do is they run a current along this direction. So now you have current that are going in opposite directions of each other, right? So they're going to push each other apart, right? What you can do with this little example, so I highly suggest you go through this example yourself, right? Is that when you, let's say, I'm standing on top of this, right? What will happen is that it'll compress these two springs, right? And that actually changes the size of the magnetic force between the two, okay? By measuring that change in the magnetic force, you can actually figure out how much weight is on this on top of the scale itself, right? And so whenever you see a little tiny scale, I think there's one right there behind there next to the sink, right? These little tiny scale, the way they work is by having a little spring, a little current loop that measures the magnetic force within the loop, and therefore you can actually figure out how much weight is on top of it. Because if you put weight on top of this, it'll compress the spring, it'll decrease the distance between them, right? So this is sort of a neat application of magnetic force. Another one, but this is a more challenging example, so I'm not going to try to go through this because it'll take me a whole lecture to go through this, is if you have a speaker on your phone or your computer or your home entertainment system, any speaker runs on magnetic forces, okay? The way that a speaker works, there's a little blurry pictures here, is that you place a coil of wire. Remember, having multiple coils increases the magnetic field, right? And you place that between two permanent magnets, one that has the north pole inside, one that has a south pole outside. So therefore, right, it creates a magnetic field going always outward from it. If I can draw that correctly, that would be great, right? Okay. Okay. If I'm running a current through this, right, this way, right, and then the magnetic force, let's say I'm looking at this one, right, this part, right, what's going to happen is that it's going to create a magnetic force that's going to be coming out this way, okay? And what that does is basically kind of vibrates the little cardboard that's on top of your speaker. I wish I actually brought one out so you can see it, right? And that vibration, right, as we learned from last semester, vibrations of air is what? Is sound, right? And that's how speakers produce sound. So if you're interested in how a speaker works, go through this example and you can actually learn how that works, okay? All right. Any questions about forces on current carrying wires? Okay. Next thing we'll talk about is another current carrying wire, but now we're going to, instead of two parallel wires or anti-parallel wires, we're going to have it run in a loop, and let's see what happens, okay? And we're going to see that, basically, multi-billion-dollar companies are basically working on this principle, right? Okay. So in this little situation, what we're going to do is we're going to place a loop, right, that has a current in it. I know it doesn't make sense. There's nothing connected to it. We'll figure out how to make the connection in the future. But this is just a conceptual thing, right? We'll have this loop. Just pretend there's some way for us to make a current in it, right? It's just going around in the box like this, okay? And we place this loop in a magnetic field like this, right, going straight up, okay? Okay. So what's going to happen to the loop? And if it's angle at some angle phi, okay, we're going to see what this phi angle is. Now this is a complicated drawing, so we're going to study this a little bit at a time. Okay, so let's say, right, I'm going to study part A of the loop, right? Every time we have a loop like this, we're going to break it up into little tiny pieces so we can study each part of the loop separately, right? Part A here, right? So we have a current that's going this way, right? We have a magnetic field that's going up, right? Therefore, the force on that is actually going to be going kind of like coming out of the board, coming this way. Does that make sense? If you point your finger like this, right? Right? Okay. So somehow, right, by placing this current in a loop, it'll actually apply a force this way. Okay. What I'm going to do is I'm going to skip to part C, right? It's going to be very similar, where instead of the current going this way, now the current is going this way, right? The magnetic field is still pointing up. So if I do my fingers correctly, now the force is actually kind of going a little bit into the board and to the right instead, right? So somehow, right, by having a current inside magnetic field in a little loop like this, you're applying a force like this, okay? Right? I wish I have a box, okay? Okay? Yeah, this will work too, right? If I apply a force this way on the book and this way on the book, what happens? What is it actually applying? It's applying a torque causing a rotation, right? So when you have this object in a magnetic field like this, it'll start to rotate this way, okay? If the only force we have to worry about is these, okay? All right, what about part B and D, right? This side of the loop and this side of the loop, okay? So on the edges of the loop, what happened is that you have a current going this way. You still have a magnetic field, but now the force is actually trying to pull it this way, right? Is it also going to rotate that way? What happened is that when you have on the other side, the force is pulling the other direction, okay? These are going to be on the same axis, so therefore it's like two forces that's trying to pull something like this on the same axis, so it's not going to rotate at all this way, right? It's the fact that we have a offset axis that's causing it to rotate only in this direction, and you pull this way and this way, it doesn't rotate, right? Okay. So therefore, what's going to happen is that when you place a little wire loop in a magnetic field with current in it that magically appears right now, right? Well, I'll tell you how we can actually create this current. Okay, it'll create a torque on it, and this torque can be calculated by just taking the cross product of M cross B, and then you may be asking, what the hell is M, right? M is actually just the current magnitude, how big that current is, times the area of that loop, okay? I'm not going to go through the math to derive it, so if you're interested in the derivation, right, it's in the textbook, okay? And the direction of this torque, right, is once again, done using the right-hand rule, where the direction of M, actually, the previous edition used mu, right, is going to be in this direction. So I'm going to actually point my thumb in it, right, and then the direction of the magnetic field is upward. So actually, what's going to happen is that you're going to have a torque that's kind of going into the board this way. Okay. So if you have a torque going this way, that means it's actually going to rotate around like this. Okay, let me draw that again, okay? I know that we need to get reminded of what torque is, okay? So let's say I have a M vector this way, and then a magnetic field going this way, going up, right? So if I do my right hand thing, we're going to have actually what I'm going to do is I'm going to orient this so it's at 90 degrees so it's easier to see, okay? Okay, so just imagine the current loop, right? This orange thing, right? Right, it's kind of like going like this, right? It's kind of like on this edge instead, okay? It makes it easier to see, that's all, okay? And then now this M vector, which is the normal vector to the area of this thing, right? It's now pointing to the left, right? V is this way, so it'll create a torque that's actually going into the board, okay? And the way you figure out, right, if you have a torque going into the board is that if you point your thumb in this direction, right, it's going to rotate around the curvature of your finger, okay? So the rotation is going to be This is clockwise. Okay. So all of this depends on your right hand. Okay. All right. So this is kind of cool, right? Just put a little current in the magnetic field, it'll start spinning around, right? If you have a superconductor, this will actually kind of just keep going, which is kind of cool. But if you don't have a superconductor, what you need to do is actually create that current somehow. How do you create current? You know, if you have to, if you don't have a superconductor somehow, right? How do you create current these days in your phone and your laptops? Well, energy in the form of what? Electric energy in like batteries, right? Right. If you have a battery, right, then you can actually create this current. Okay. So this is how an electric motor works. Okay. So electric motor is usually like a little cylinder, right? And you hook up the power supply to the end of the motor. These wires here connects to basically winding inside the motor. I'm going to show you a better picture of it right here, right? Okay. Where this is sort of like a simplified picture, usually it's, you know, a circular shape, but it just makes it the geometry so you can easily understand it, okay? So this is a very similar situation what we just described up top, where you have a box, right? A box shape inside a magnetic field, right? So what's going to happen is that this little shape was going to start rotating if you have a current going inside it, okay? But what happened is that, okay, once it rotates this way, right, now the normal vector, instead of pointing out of the board like this, is going to point into the board, right? Every time you rotate, right, let's say, do my little Voyager satellite picture, right? If I rotate it this way, right, the normal vector used to come out this way. If you rotate it 180 degrees, it'll point into the board, right? So now the torque is actually going to be reversed, right? So what's going to happen is it's going to try to do this, right? And the fancy trick is, what you can do is put a little, these are going to be brushes, this little connector here, so that when the current loop is pointing this way, you apply current going this way, but once it flips, you flip the current around by just changing the direction that the battery is connected, right? So it actually applies the same torque in the same direction over and over again, and that's how you keep a motor running as opposed to just jiggling back and forth, okay? Okay, so this is kind of a cool little thing, right? And all this stuff was kind of figured out in the early 1800s. In fact, the first electric car was made in 1839, about 50 years before the internal combustion engine car was made. Because electric car is actually much simpler compared to, you know, the engines of your car and all that burning gas stuff, okay? Okay. So, you know, you just had like, you know, 10 packs of 9-volt batteries down here, right? And then a little electrical motor here, and it's like a little drive. And then it looks like a little tricycle, but, you know, it works, okay? And this was made by Robert Anderson in the US in 1839, okay? The first electric motor was made by this Hungarian person, and this is actually the motor itself. You can kind of tell what it's trying to do. So you have the magnets here, right? And then you have the current loop. Sorry, you have a current loop this way, going over and over. Remember, doing multiple loops allows you to magnify either the magnetic force or the current the magnetic field it creates, right? And I think these are the permanent magnets, and this is the current loop is actually trying to go around. I think in this case, they kept the loop stationary. The magnet is the thing that can rotate instead, okay? Because I think it's easier to make the connection like that. Okay, so that's how a motor works, okay? Let's see, got another 15 minutes. I'm gonna skip the part on the Hall effect. The Hall effect basically allows us to measure the charge of the particle that is moving. Is it positive or negative? And if you're interested in it, really look in this in the textbook, because it's just kind of a free body diagram problem, okay? But since I don't want to go over time, I'm just going to talk about the next part of the chapter. which is the last part, which is the magnetic properties of matter. Meaning, why are things magnets? Why are some things magnetized, some things are not? And if you feel like not worrying about this section, I didn't assign any homework. I'm not going to have a test on it. So this is just kind of for your FYI kind of section, okay? And if you are majoring in physics, you will learn this much more deeper when you get into modern physics next semester. Okay, so what we discussed so far are mostly electromagnets, meaning you put a little battery, right? You make a little battery, you run some current through it, right? And then and voila, you can get some magnetic field out of it, right? So in this case, right, the magnetic field will be going outward, coming in, and so inside the loop you have a magnetic field going in to the board, right? Okay, but there are things that are natural magnets, such as these, right? These are, I don't know what these are made of, but these are freaking hard to pull apart, right? Right, so that's not magnetic. One of these things are. They're not, but this stuff is, right? Right, so you have magnets that are not current, right? There's no, I didn't, make a current in there, right? So how do natural magnets, or also known as permanent magnet, work? So why are some things magnets, some things are not? Okay, so this requires us to understand the atomic physics of things a little bit, right? So hopefully most of you guys will trust me that atoms are made of nucleus, and there's an electron cloud that's kind of orbiting it, right? This is a simplistic picture. Wait, which way is this actually going? Right, so the electron is going this way, so the current is actually going the opposite direction because of what? Because of what? Because of, yeah, it is his fault, but because the electron is actually negative, right? So a negative charge going this way is the same effect as a positive charge going the opposite direction, right? So that's one of the key things we should know, okay? So what happened is that as these electrons are spinning around, you're going to create a current going this way. And remember, when you have a current going around a circle, right, you create a magnetic field, right? So in fact, you can actually figure out the direction of the magnetic field, because if your current's going this way, it's going to create a magnetic field pointing up, okay? And this little mu letter is known as the magnetic moment, okay? So this occurs, right, if you have an electron spinning around your atom, right? So but those of you who are in chemistry, right, what are the usual shell number of electrons per electron shells? Do you guys remember that? Right, the first shell has how many electrons in it? It has 2, right? That's the S, right? Right. So usually there's actually 2 electrons in it, right? And the electrons are actually going in opposite directions from each other. I don't know how to do that. Okay. So what happened is that, let's say you have, what's a good example? Let's say you have a helium atom, right? That has 2 electrons, right? One electron will be going this direction, electron number 1, right? And then there's electron number 2 that's going in the opposite direction. So the 2 electrons actually creates an effect that it has no magnetic field. So therefore, helium is not magnetic, right? Because it has a an even number of electrons in its outer shell, okay? But some other, I wish you have a periodic table in here, right? For example, iron and nickel, right? These are highly magnetic elements. The iron and nickel has what's known as an unpaired electron. So the electron shell structure of a iron and nickel is more complicated because there's just so many electrons around. But then once you get to the outermost shell, there's actually just an extra electron around that is not paired, right? This unpaired electron is actually causes the reason why iron and nickels are magnetic, okay? This is the reason why, so when I was playing around with this, right, I think this is made of aluminum, and therefore it's not magnetic, and that's because aluminum has pair outer electron shells, and whatever this is, neodymium, I think it's a pretty strong magnet, against probably this iron here. Um, Iron has an unpaired electron in the outer shell, and that's why it actually interacts with magnetic field. And okay, so when you have basically electrons orbiting around nucleus, right? What you're going to have is you're going to have magnetic fields just created by the fact that they are electrons that are unpaired around your nucleus. Okay, so I think this is not in the textbook, but I just want to dive into this since I'm a particle physicist. I love this stuff that goes deeper and deeper and deeper, right? Not only do atoms have spins, creates magnetic field, elementary particles themselves creates magnetic fields, which is weird, right? Because remember the thing I told you is that, oh, in order to create a magnetic field, you need a charge going around a circle, right? Right? But if you have electrons by itself, right, it's not going around anywhere, right? It's just an electron by itself. If I just give you an electron, it'll just be sitting here, right? It's not going anywhere compared to it. Even elementary particles themselves have this property called a spin, okay? And the way people try to picture this is that it's as if the electron is just spinning around its own axis, okay? And you may think, oh, that's not creating a magnetic field, right? Because it's not a current, right? The charge is just spinning around itself, right? But that also creates a magnetic field around itself. And I'm not going to dive too deep into it, but so far, right, as I stated before, we're not able to divide up, electron into half to make a north pole only electron and a south pole only half electron, right? So we have not found this thing called magnetic monopole yet. And so, and whoever find it will probably win some sort of, Nobel Prize or something like that. But this is something that we're actually not able to find yet. And so far what we can measure an electron to be, we cannot break it up into two different little poles, okay? So going back up, right, from the atomic view, right, let's go bigger, right? So if you have a bunch of atoms together, right, why would some of the stuff be magnetic, such as this little permanent magnet here that I'm trying to peel off? Oh, there it goes, right, right, right. And then just other, iron. Why is this piece of iron, right, magnetic, but this piece of iron, so sorry, why is this piece of iron, it interacts with magnetic field, but it's not a magnet itself, and why is this little piece of iron a magnet, right? Okay. So in general, right, let's say I just have you guys, let's say you're at a party, right, and people are just talking to each other. Everybody's just kind of like facing in different directions, right? And that's how atoms are also. In general, right, all these atoms, right, are facing in random directions, right? Right? And the average number of random things is actually 0, right? Right? So in random situation, right, all these little atoms that have these magnetic moments that I just kind of conceptually taught you about, right, they have a random direction to it. So therefore, even though they are susceptible to magnetic fields, they create net magnetic field of 0, right? Because this this magnetic field will cancel out this magnetic field. This magnetic field, right, will be canceled out by this magnetic field. So overall, you get 0. Okay? So the reason that some objects are magnetic, called ferromagnetism, right, especially iron and nickel, okay, is because they are actually created inside Earth's mantle in a liquid form. Why is it important for it to be in liquid form? When you have something that is solid, right, the orientation of all those atoms are already fixed. You cannot rotate them around. But when you have a bottle of water, right, all those atoms are actually free to rotate around as they like. Okay? So when you have a permanent magnet like this, what's happening, and you can solve this using this thing called an icing model, okay? So if there was no preferential direction of the magnetic field, all these little tiny magnets inside your magma, right? It's going to be in random direction. But let's say you have some magnetic field, right, while this little magma in liquid form is inside the Earth, right? Where would this magnetic field come from on the Earth? Sorry? Yeah, the core itself, right? Our entire planet is a giant magnet, right? So the fact that we have a rotating liquid core with a solid center, right, creates a magnetic field, and that actually creates permanent magnet naturally. So these are called natural magnets. And because when the iron is in its liquid form, right, all these things can rotate, right, all of them will tend to align with the magnetic field, and these are called domains of your material. So when you apply an external magnetic field to a liquid, you will align all of those magnetic fields, okay? And that happens inside our planet. And this is the reason why, right, people just started discovering magnets, right, just by picking up rocks, and sometimes they stick to each other, sometimes they don't, right? And that's why, like, a lot of magnetism, like in China and in ancient Greece, this is where there's a lot of volcanic activity, right? When you have volcanic activity, you got new rocks that comes up, right? And these rocks, as they solidify, right, instead of going back to its random direction, when a rock solidifies, all these gets locked in place, and now, right, now you have a permanent magnet, because all of the, even when you remove this magnetic field, now it generates its own magnetic field, right? Right. So that's how permanent magnets are created on Earth initially. Okay. So as magma comes up to the surface called lava, so I'm gonna get all these geological terms incorrect, and it cools, it turns into rocks, and you get permanent magnets. And people just chip off pieces of this, and do a little cool demonstration by throwing magnets on the walls. Okay. All right, so that's how natural magnets gets created on Earth. Nowadays, of course, we can make artificial magnets instead of making them out of iron nickel. I think the magnets I was playing around with are actually made of neodymium, which actually has multiple pairs of unpaired electrons on its outer shell, and then you can make really strong magnets, such as those. You can hang people on them, right? And let's see, is there anything else? Oh, you can actually create your own magnets if you just take a little piece of metal. This is going to be kind of weak, even if you have a strong magnet, right? So you probably did this I don't know if you guys ever done this in your school, where you take a magnet and you just rub a magnet to a piece of metal over and over and over again, right? And after maybe 10 minutes of rubbing, this will be slightly magnetic, okay? Because even though these iron atoms are locked in place, you can still kind of wiggle them a little bit, okay, to make them align with the magnetic field. So you can create magnets out of ferromagnetic material by basically, rubbing a little magnet on top of it. And you want to make sure you're rubbing it at one of the poles, because if you're rubbing it with both, then you're just kind of, randomizing things, okay? And you can make a little, in case you ever get lost in the forest, you can make your own compass by putting a pin on a piece of wood and on top of some water, okay? All right, so I'm actually said that this was going to be a shorter lecture, which I